Hi, my name is Matthew Gilbert. I'm a sophomore in computer engineering at VCU. I've been on the AUVSI team for 1 year. My role in the AUVSI team has been mostly mechanical building. At the competition, I will be doing image processing.
I am AUVSI. I am a graduating senior mechanical engineering student. I have been working mostly on the mechanical build and doing some of the electrical on our entry. I have experience with UAVs in that I've been working with remote control cars and remote planes for a long time, and I also build drones and UAVs in my free time. I'm hoping not to be doing much repairing during the competition, but I'll also be probably doing some of the visual recognition. We are the VCU UAV team.
My name is Bob Clanky. I'm a professor of electrical and computer engineering. The faculty advisor and safety pilot for the VCU AUVSI team. I've been attending the competition since 2003 and been flying UAS both recreationally and professionally since about 2000.
My name is Lauren Linkus. I'm a junior at VCU studying electrical engineering and physics. I've been on the AUVSI team for 1 year. I wrote software for the ground control station, and I'll be doing image processing of the flight line.
My name's Andy Payton. I just graduated from VCU and I started grad school here. My interest in UAVs came out of being an RC enthusiast and getting into the computer engineering program at VCU. So that attracted me to flight controllers. So my role on the team has been primarily flight controller development. And on the flight line, I'll be operating the GCS, setting waypoints and airspeeds and things like that.
Hi, my name is Peter Truslow. I'm a junior here at VCU, and this is my first year on the AUVSI team. My development for the SUAS competition has been primarily focused on developing our flight controller and tuning that up so we can fly as well as we possibly could, and also building our interoperability system. I also fly racing quads and planes a little bit as a hobby, and I've been working with UAS for right around a year. On the flight line, I will be manually identifying targets in images that will be sent down from our UAS.
Hi, my name is Mike Penny. I'm a senior in electrical engineering at VCU. This is my first year on the AUVSI team. I've been helping develop the flight controller for VCU, and for the competition, I've been mainly working on waypoint navigation. On the flight line, I'll be working on image processing.
Hello, my name is Berkaya Manabrahan. I'm currently a junior at VCU studying computer engineering. It's my first year in the AUVSI team, and I'm working on image capturing system autonomously. And during the flight line, I will also be working on the autonomous image capturing system.
The plane that will be flying at the competition is a 2.6 meter Cherokee plane made out of plywood. It has a 21-inch propeller, and it's flying a 12S 12,000 milliamp hour power system.
This is our flight control system. VCU has developed and maintains its own flight controller, which is this board. It's called the Aries. It's gone through several revisions. The current version has a STM32 ARM processor in it, the main processor as well as a safety processor. We've got 900 megahertz radio. We've got several barometric sensors for altitude and airspeed. And then we're also linking to a Pixhawk Mini, and we're using that as a position sensor to get its Kalman filtered position and altitude data. So one of the major parts of our payload is the camera system. This is composed of our Sony Alpha camera. It's a 24.3 megapixel sensor compact DSLR camera. That's mounted to a 2-axis gyro-stabilized gimbal, and that's attached to this linear actuator to extend it down and out of the airplane body while we're in flight. The circuit board to the left of the camera is the gimbal controller. The camera is controlled also by a beagle bone, and the beagle bones are compact computers installed in the upper level of our payload system. Once the data gets to the beagle bones, it'll go into a queue and be broadcast to our ground station as quickly as possible for additional image processing. So we had an egg dropper from 2 years ago. Are we using that again, or what's the plan for this year?
So here's the original egg dropper. It consists of a tube, a trapdoor on the bottom, and 2 servos. Mm-hmm. One of the servos is controlled by the safety pilot as a safety. The other one is controlled by the beagle bone, so when it releases, the trapdoor will open and the egg dropped out. So that design is going to be modified with a much larger tube that will be able to fit the standard 8-ounce water bottle.
Okay. And how are you going to protect the water bottle so it survives the impact?
We've got a couple of different designs in mind to protect the water bottle. One idea is to wrap the bottle in duct tape. This will ensure that the cap stays on, which we've found to be the leading cause of the water being released. We are not sure yet exactly how much duct tape needs to be used. Here's another design with less tape. Another option we have to protect the water bottle is building a cone around the front of it with spray foam insulation as padding and some sort of parachute behind to make sure that it stays pointing downward and to help slow it down a bit. We have software in the beagle bones that will help us calculate and estimate at each point if we drop the water bottle how close it would get to the target, and that will automatically decide when to drop the bottle.
So this is our flight simulator and ground control station. This is a real GCS on the right, and this is flight here simulating flight on the left, feeding flight data, position, altitude, and pitch and roll and all that stuff into our actual flight control system that's just running in software instead of in hardware. So when we're working on our flight control system, we've got a couple of levels of simulation we can do. This is what we spend most of our time in, which is the software in the loop simulation. We're running our actual flight controller code, we're running our actual ground control station, and we're using a flight simulator to simulate the physics of an airplane flying around. We can do that for stuff like testing code changes to our flight controller, and also for tuning up our airplane to do waypoint navigation and to cross-track as accurately as precisely as possible.
Okay, many of our tests started in the simulator prior to real-world test. Our autonomous takeoff, flight, and landing started using a modified version of flight gear before moving on to being tested on the actual aircraft. Waypoint accuracy was tested in the simulator as well as in actual flight. Obstacle avoidance was tested using the simulator and then was also moved on to be tested in actual flight. Our image detection, capture, and localization was tested using test images prior to being tested on the aircraft. Air delivery was tested by dropping the package from a height of 70 feet and will be deployed from a higher altitude during our next flight test.
Okay. This is the autonomous object recognition and classification system. To the left, we have a test image including 7 targets with different shapes, color, and alphanumerical character. And once the system is run, it is able to detect and locate the actual shape, background color, foreground color. And once it is able to do that, it is sent out to the server, the secure server, which then it will be sent to the interop system for submission.
Our collision avoidance system can be seen tested in a simulator here. Given a set of waypoints and obstacles, it is creating intermediate waypoints which will be sent to the flight control system aboard the UAV.
This is VCU's second year at the AUVSI competition using this Cherokee airframe, and so we've got a lot of auto flights on it, both from 2 years ago and from recent flight testing. We couldn't put a number on it, but it's many dozens, I'm sure. Generally, we'll take off in manual mode, and then we'll switch to auto as soon as we've got up in the air, and we'll stay in the air for about 15 minutes under auto mode, and then come back and land in manual mode. For tuning, we have our flight controller lets us remotely choose a set of data streams to output at a high rate. And so we can focus on one of the PID controllers, all the internals of that, and then dial them up and down remotely while watching both the macro effects of how they affect the airplane dynamics and the micro effects of watching the traces on our graphs of the individual calculations going on within the processor. With that system, we've been able to really tune up the aircraft to a pretty high degree.
To test our bottle drop, we created several prototypes of the water bottle with the foam nose cone and dropped them from a height of about 70 foot onto concrete. We found that all of the prototypes survived the fall, and next time we go flying, we will have the water drop mechanism built and attached onto the plane so that we can drop water bottles from a higher altitude and see how accurate our dropping algorithm is.
During our most recent flight testing, our waypoint accuracy was between 50 and 150 feet, depending on environmental factors as well as how close waypoints were placed to each other. Waypoints with a greater distance between them resulted in improved accuracy, as our cross-tracking algorithm was able to follow the line between waypoints more precisely. As we continue flying our plane autonomously, our waypoint precision will improve with more precise PID values.
We started this year, and we wrote in our technical paper that we're using a VTOL modified aircraft, a fixed-wing aircraft that's modified to have a vertical lift capability as well through a quadcopter-style multi-rotor system. That's where our development for AUVSI started. We had to modify and build the aircraft. We run our own flight controller, and our flight controller didn't have that level of capability in it yet. So we had to work on getting the quadcopter system to a point where it's fully autonomous, to where it can do GPS control, altitude control, and automatic navigation and return to home. And we got all that stuff done. That took a lot of effort, and when we flight tested all that, and we've gotten through all of it. One of the interesting points along the way where we had to stop as a result of our flight testing and do some rework was when we started getting the results of our position and altitude test back. We're using a barometer for altitude, and we're using GPS for position, like I'd imagine most teams are. One of the things we figured out was that just reading those sensors isn't good enough, that we have to integrate the data from the raw sensor along with other data sources, like the accelerometers telling us how the vehicle is moving, in such a way that each data source makes up for the inadequacies of the other ones, and you end up with a pretty good estimate. That's a level of sophistication that we couldn't do during the cycle of this competition. So we've added a second flight controller to our system, which is the Pixhawk that many of the teams at AUVSI be familiar with. We're not running it as a flight controller, but it's up and running, and it's doing its very good position and altitude estimates, and it's feeding that data to our Ares flight controller. So now we can use our GPS control, our quadcopter control, but with the Pixhawk as a data source for it, and that works out really well. And so that was the point where the VTOL aircraft could really take off. We can fly it as a multi-copter, and we got to the point where we started working on our transitions from vertical flight to forward flight. During one of those transition tests, we had a pretty bad configuration error, and when we flew up to about 200 feet vertically, and then when we transitioned to forward flight, as soon as the multi-copter motor shut down, the aircraft pitched down to about 90 degrees, and then at some point it pulled up just as hard, and it pulled up suddenly enough that it snapped the wings in half, and the plane fell about 200 feet and just like shattered all over the ground. So that was the end of our VTOL aircraft for this competition cycle. We're definitely going to keep working on it. But that meant we had to go back to Plan B pretty quickly, and Plan B is the Cherokee aircraft that we've run in AUVSI 2015. So we've fitted all of our new equipment into that and got it up, got our safety pilot hours on it, got our autopilot proof of flight videos and whatnot on it. And now we're at the point where we're doing our payload tests with the camera system, the gimbal, the airdrop mechanism. And so we're getting to the point pretty soon where we can take the data from that and then start doing full mission tests.
For our projected score calculation, we went through each of the components and estimated the score we expect to get. So for the timeline, we're expecting to have about 18 minutes in the air and up to 20 minutes of post-processing, which gives us a combined score for this event of 57%. For autonomous flight, we are assuming that we won't be able to make the autonomous takeoff or landing, and we are assuming that we'll be able to get with an average of 25 feet within each waypoint, giving us a score of 75% for waypoint accuracy. We're assuming that we'll be able to avoid all of the obstacles without any issues, so we'll get the full points for that section. For object detection, classification, and localization, we're not sure if we'll be able to detect all of the objects autonomously, and we're expecting to be able to geolocate them within about 50 feet, giving us an overall score of 82%.
For air delivery, we are hoping to get the water bottle within about 50 feet of the target, giving us a score of 66.7%. And for operational excellence, we expect to get the full 100%, giving us a combined score of 72% of the total maximum points.